All right, so the moment we finish, please check if the live is visible. I think the live should be visible. I think our live should be very much visible. Just check for me if our live is visible. I think it is. All right. So now, what we're going to do is soon after these live videos, when I finish them, I'm going to put them on our website and you can access them. Are we together? So this type of lesson that we are doing is called a note-taking lesson, where I give you all the information you need. Then we are going to have the revision sessions where we are doing questions together. Are we together? Do you hear me? In here, I'll just give you one or two questions, a few questions that I may solve with you. But when I'm going to completely focus on questions, it's going to be in the revision session. So this is the note-taking session. For before you do any revision or whatever, you need to learn about something first. After you learn about it, then now we can do questions. Victorson, do you hear me? All right, good. So now what you should know is that we are trying to go, okay, for stage 9, okay? Stage 9 science, we are preparing for, this is for stage 9 students who are preparing for checkpoint exams, like you, Vic, and AT. So stage 9 science has 9 chapters, okay? Stage 9 science has 9 chapters. And what we know is that those 9 chapters, 3 chapters are for physics, okay? Science is broken down into 3. Into physics, chemistry, and bio, right? Physics has 9. Physics has 3, I mean, out of the 9. Chemistry has how many? 3. Then the bio part of science has how many chapters? 3. So these are combined to give you science, which is how many chapters? Can you answer? Are you hearing me or you're not hearing me? Right, so we were saying that what they call science for us, we know that they have just combined 3 things into one. They have combined bio, they've brought chem, they've brought physics, they bring it into one and they call it science. And they say, you must know this. So, okay, when we are knowing it, when we are learning it, we are going to separate it. We do physics, we do chemistry, we do biology. We are doing all 3 at the same time. But you must know, this chapter is part of the 3 for physics. This one is part of the 3 for chemistry. This one is part of the 3 for biology, okay? I'll give you all 9 chapters. I'll write them before our bio lesson or our chem lesson, and I'll show you the ones for bio, the ones for physics, and the ones for chem. Are we together? All right. But as of now, we continue. As of now, we are moving. So what I want you to do is, we are starting chapter 6. Today we are doing chapter 6, which is from physics. Chapter 6 is from physics. Chapter 9, electricity, is from physics. So here we are doing chapter 6, which is sound and space, which I said is the same thing we are also doing with your seniors. We are doing space physics, which is chapter 6 for your seniors, for physics. So this is good. Can you all write sound and space quickly? That's the chapter we are doing. It's a physics chapter. It's chapter 6. That's the one we are doing today in our lesson. Are you ready to start? Okay. What I want you to know is that this chapter will have 3 sections. So we're going to quickly go through each section one by one, and then we'll see how it is, okay? This chapter has 3 sections. We'll do section 1 right now. Can you all write section 1 is loudness and pitch. We want to understand sound and space. So we start by understanding loudness and pitch. The syllabus wants you to understand loudness and pitch. Can you write 6.1? Loudness and pitch. This is 6.1. Loudness and pitch. After we know loudness and pitch, we go to the next thing, then you go to the next thing, you go to the next thing. So let's see what you must know. Okay? Let's do a quick background on sound. What is sound? Sound is produced. Sound is produced when objects vibrate. So basically, sound is a vibration. If I'm speaking like this, making a sound, if I hold my neck, I'm going to feel it vibrating, because sound is a what? Sound is a vibration. Have I made myself clear? Students, sound is a what? Sound is a vibration of objects. Okay. So sound is made when objects vibrate. This is more of a chapter 7 thing, but we'll still move with it. This is more of something that you would have learned when you were doing stage 7 or stage 8. Right. So, but you can still write it to say. So sound is produced when objects vibrate. Sound is made when objects vibrate. Are we together? Let's put examples. Examples of vibrations. You can't have sound without a vibration. That's not a negotiation there. If you want to have sound, you have to be able, you should produce a vibration. For example, guitar strings. Okay? Example number 1, guitar strings. What do? They vibrate for you to play your guitar. Right? What else? A drum skin. The surface of it, you beat it up so that they vibrate, so that it vibrates. If you want to make sound from a ruler will vibrate when flicked. So all these things will be producing a sound because there is a vibration. So in your vocal box, by your neck there, where the sound is produced, there's serious vibrations there, because sound is made or produced when objects vibrate, when there is a vibration. Okay? So you should write vocal cords. Vocal cords vibrate when speaking. When you are speaking, vocal cords vibrate, and that is how sound is made. So all of us are agreeing right now as a class that sound is made when objects do what? What should objects do for us to get sound? What should they do? They should vibrate. If there is no vibration, will there be sound? So if you are whispering, is there much vibration there? When we're whispering, do we have a lot of vibrations? No. That's why there's not much sound. If you want to have sound, vibrate. Hey, man. No. All right, man. These vibrations, that's why there's a lot of sound. Okay? So what happens with these vibrations? These vibrations cause air particles. The vibrations that you are doing in the vocal cords, they cause air particles to move. The vibrations you're doing with your guitar string, they are causing air particles to move. Okay? To move forward, to move forward and backwards. Okay? Creating a wave, which is a sound wave. So, creating a sound wave. So, the vibrations, they also cause the air particles to vibrate. And there's a wave, and that wave is a sound wave. So, sound is a vibration. If you want to produce sound, there must be a vibration. Okay? So, sound is made when objects do what? Yes. Here's a diagram. Let's say you have a speaker. Just to show, it's a simple thing we're trying. We're just showing that sound is made from vibrations. Oh my days. There we go. And let's say there is an ear here. Okay. And let's say sound moves like this. And you say here, direction of sound wave. It will be moving like this. What do we know? Here, this cone, what is it causing? How do we have sound from this, boys? How do we have sound from the speaker? What is it causing? Vibrations. Yes, when something is a vibration, it means you go forward, backward, like this. You're going forward, backward, forward, backward, forward, backward, forward, backward, forward. That's a vibration. So we know that sound is going to, for us to have a sound wave, then we must have vibrations. Are we together? Are we together? So here you are going to show vibration. Okay? This sound wave, I want you to draw when you put the dots. Some part put a lot of dots close to each other. Then in some parts put them spaced out like this. Okay? In some parts they are close, in some parts they are spaced out. Are we together? In some parts you have a lot of sound waves in one area like this. Then in some parts make them spaced out. Then in some parts make them close to each other. This is called a compression point. Then when they are spaced out, we call it a rarefaction. Then we have another compression. Are you seeing it, boys? Yes. So the vibration of air particles. Vibration of air particles in sound wave. Have you written it? So the movement of your air particles here, the movement of your air particles here, you're going to draw it like this. I want you to know that we said sound causes vibration of air particles, right? And that's how you get a sound wave, right? So there's a vibration which causes also the air particles to also vibrate. That's how sound moves. That's how it's moving from me to you. Okay, I produce sound in my vocal cords, then the air particles will be made to move. The vibration started on the neck there, the vocal cords, but now the air particles will also vibrate, carrying this sound to the ear. Here is the ear on the other side, and that's you. To get to you, the air has to move. Are we together? I say, hey, I'm shouting, and people hear me. How did they hear me? The air, the sound wave moved through air. Now that means when the sound is moving, the wave will be just moving nicely like this, the sound wave. But the air particles, not the wave, the sound wave moves nicely, but the air particles, they move like this. That's how they carry the sound. They go backwards, forward, backwards, forward, backwards, forward. As they are moving towards you, they take a big step forward, they move back a little bit. Step forward, back. Are we together? Back forward, back forward, back forward, back forward, back forward. Hitting each other, hitting each other. They hit each other and they pass sound from me to you. They hit each other and they give each other that sound. Are we together? So what I want you to know, I want you to write to say the movement of particles in the air is difficult to draw. The movement of the particles in the air, we can show with an arrow to say they go back and forth, but it is difficult to draw in the sound wave, like what we'll be trying to do. The movement, we want to show how the particles are moving. It is difficult to show in the sound wave. Okay? But it is easier, okay? But is easier, the movement is easier to draw in a graph. The shape of this graph, which shows movement of particles with time, how the particles are moving, the shape of this graph is sometimes called a wave form. What is it called, boys? Waveform. What is it called, Vic? Waveform. What does it show? Movement of particles in the air. So from today onwards, I want you to know that the movement of particles, we know that there is a vibration. That vibration is shown on a graph, and that's called a waveform. Okay? Like this. And I want you to say this is amplitude. This is the wave. This is called amplitude. Amplitude is the distance from this line here to the top or to the bottom is the same. Okay, this distance is the same as this one. It's called amplitude. So when they're asking amplitude, they're asking you to start at this line here, which is the line we call the equilibrium line. If they ask you, they're asking you to start at equilibrium line here in pink. If they ask you for amplitude, you start at the equilibrium line, then you go to the top or you go to the bottom. What we are drawing is the waveform. Yeah, the graph which shows the movement of air particles. They go up, they go down, they go back and forth. They're going back, forth, back, forth. So here it is going forward, then backward, then back to its original place. So it goes forward, then back to its original place, then it goes backward, then it goes back to its original. Are we together? So this side here, this is time. This other side is distance moved by particles. So we are showing the distance that is moved by the particles as time is moving. And this is forward motion. And this is backward motion. Are we together? Good. And that's what we call a waveform. So amplitude, let's see if they ask you on your waveform. What is waveform? It is showing you a graph. What is that graph? It's showing the movement of particles in the air. Are we together? How they move with respect to time. It doesn't show you the direction, but it just shows you how they move. This one is forward, their movement forward. Then here they are back to zero. Then their movement backward. Then back to zero. So they go forward, back to the start, backward, back. That's how you go forward. Boom. Isn't if you are vibrating, it's like you are going like this. It's like you are swinging, huh? You swing up to this point, then back. You see? This swinging, swing back, swing back. This is the origin. This is the, we can say the rest. Started here. Then it goes backward. Then it will go back to the zero. Okay, it will go backward, then back to zero, then forward, then back to zero. Are you seeing? And that is the vibration. Wum, 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 wum. It's continuous. It doesn't stop here. When it gets back to zero, it doesn't stop. It will be continuing. It's swinging. It's swinging. It continues. It doesn't stop at zero. It continues to get to the other side. Okay? Then it swings back. So it continues to get here, then swings back. Okay? Keeps swinging to the top. You understand? This is what happens. Okay. Let me see. Right. There's an emergency. I'm sorry. Right, everybody, are we together? Can you see? Right. So if they come and they say, "Hey, what is a waveform?" You say it's a graph. Waveform is just a graph which shows how the particles move in air. Okay? In a sound wave. We know that they vibrate. They don't go in one direction, they'll be just vibrating. Again, because sound is a vibration. So I don't know what you want if you don't want a vibration. I don't know how you expect to get sound. Are we together? So if it's as long as there is sound, we need to see this graph going up and down and up and down, and the line will be like this. We know that there's a center line somewhere at the center here. And because it's a vibration, it's showing you that the particles are moving. So, oh, the particles are vibrating, yes. Oh, so there is sound, yes. Come on now. You see, boys? Are we together? Yes. Are we together, Mr. Vic? Good. Sound is a what? Is a vibration. Yes. So you, when you see it on a graph, it will be what type? What is this graph called? When you show the vibration of particles in the air, what is the name of this graph? A waveform. It's called a waveform. Thank you. It's called a waveform. A graph which shows the movement of particles in the air, which shows that sound is there, right? Which shows that there is sound. Now the amplitude, which I just showed you, this amplitude is the maximum distance the particles move, the maximum distance that the particles move, either forward or backward, right? Either forward or backward. Okay, in a sound wave. That's your amplitude. The maximum distance that the particles move. And you can measure it in two ways. Here, either you do backwards, okay? You're measuring from the zero to the maximum position, the lowest point. We call this a trough. From zero to the trough, or from zero to the peak. From zero, here is the zero line, to the peak, or from the equilibrium to the trough. So amplitude is distance from zero to peak, or from zero to the bottom or to the trough. Okay? You can do that, you will still get max. Are we together? To say amplitude is distance from zero to peak, or from zero to trough. Can you hear me? Trough is the lowest point, which is still maximum distance, just in another direction. This lowest point just means we are swinging backwards like this. So the last point that it reaches, this one, this is going to be your amplitude if you measure it from here, from zero. Or the last point that your string reaches here is your amplitude when you measure. So this is amplitude. If we're looking at something which is swinging, this is amplitude as well. It's the same. Either you go backwards or you go forward, you still get amplitude. Are we together? So when you're showing it here, you say amplitude is to the top or amplitude is to the bottom. Don't let me down. Don't you let me down. Peak is top, trough is bottom. Right? Yes. Are we together? Are these distances different or they're the same? They're different. The amplitude when you go to the top, to the peak, and the amplitude when you go to the trough. It has to be the same because it represents the same thing, amplitude, right? It is the same. So I want you to say both these distances are equal. Okay? Both these distances are equal in a graph of the same sound wave. Okay? Are we together? Now, now do for me this. Let me put a let me show you a picture right now. Give me a second. I want to quickly show you a picture. Hold on. Want to quickly show you an interesting picture of something that I'm now about to teach you about. Right, let's go to see this picture. I want you to see a picture. Okay, it did not come out nicely here. Can you see this? It's not coming out nicely. Mm? But you can see. Can you see? Okay. Can you see the microphone? And can you see that there's a wave in the diagram? In that machine? This machine is called a cathode ray oscilloscope or just an oscilloscope. Are we together? Yes, you can just call it oscilloscope. Right. Or cathode ray oscilloscope. Right. What it does is it catches sound and it produces these waveforms we were talking about. Okay? Are we together? It catches the sound. You'll be producing sound, producing sound, producing sound. It catches that sound and represents it on a diagram. And that's the waveform, that graph inside here. We all know We all know that graph. We've been talking about it. To say that graph is just telling us about the sound. Okay, it's just showing how the particles in the air are vibrating, right? The microphone is catching it. The microphone is catching the sound, which means the vibrations in the air. And that oscilloscope is showing you on the screen. It's giving you the waveform. Are we together, students? Victorson, are we together? So let's talk about it. Let's put it now, since you now know. Let's write here now. Everybody, can you write with me? We are continuing. Okay? We are saying. Now we are saying that. Let's write. Now we are saying. Write with me since you have seen the diagram. An equipment, or you can say an oscilloscope, is a piece of equipment that displays waveforms. It displays waveforms of sound waves. It displays waveforms of sound waves. Are we together? Yes. It displays waveforms of sound. We know that. We've seen the diagram. We know it's displaying waveforms of sound waves. That's not a problem with us. We know that. Okay? An oscilloscope uses a microphone. It uses a microphone to detect sound, like we have just seen. It uses a micro to detect sound, and then produces a waveform, of the sound on a screen. So it's going to catch with the microphone, catches the vibrations. Then it shows you what's happening on the screen. So you as a person can see, you look at the photo on the screen, you look at the graph on the screen, and you'll be able to analyze it. Okay? Are we together? So we are going to now learn how do you look at the graphs and how can you explain to people what's going on with the sound, okay? By looking at the screen of this oscilloscope. Okay, you look at the graph it's producing. Are we together? Good. So you can show the microphone. It'll be taken from here. There we go. Microphone catches the sound, then comes to show on the screen. We know the graph continues on and on and on. Okay. It will be just going on down and up and down and up and down and up. Okay. It can have your lines or whatever it's going to have. Then you can have your thing. Here's your oscilloscope. It's showing you the graph. Are we together? Here's your oscilloscope. It's displaying. It's showing you. It is connected to the microphone. It's showing you what's going on. Wow, this is great. How great is this? This is good, huh? So why are you wasting our time telling us about this? Because we are coming to something that is going to be on the graph. And that's the first relationship. So an oscilloscope is a device. It's a piece of equipment. Or you can say a device. Let me open. Huh? An oscilloscope is a piece of equipment, or you can say device. Instead of piece of equipment, you can say a device that displays waveforms on a screen, or you can say sound waves on a screen. But it displays these sound waves as waveforms. An oscilloscope will display sound waves as waveforms. As waveforms. So now we want to look at loudness. How do you see loudness on an oscilloscope? How do you see how loud the sound is by looking at the waveform on the screen of an oscilloscope? How do you see how loud it is? Okay, here is the oscilloscope. It will be doing like this. You've done a diagram. Now we are going on to what your syllabus wants you to know. We have given you the background information. You are not done. No, you are not done. Well done for all this, but you are not done, my friend. You now have to get into the real hard thing. So listen now. This is important. Victorson, are you hearing me? Vic, 80, can you hear me? We are going into an important part. First part, loudness. Okay, because we have first proved that sound is a vibration. And we have proved that this vibration causes particles in the air to also vibrate. So, first of all, the first thing that vibrates is the thing that is producing the sound. Is it a guitar string? Is it a drum? Is it the vocal cord on your neck? What is producing the sound? Whatever is producing the sound vibrates first. Then after it vibrates, those vibrations move into the air. Particles in the air also vibrate. The particles in the air are vibrating because they are transmitting sound. Now, the vibrations in the air are hard to show, but you can show them on a special graph called a waveform. Here it is. And this special graph called a waveform, you can be shown by an oscilloscope. It's a device that catches and displays sound waves as waveforms. What are waveforms? A special graph that shows the air particle vibrating, the vibrations of an air particle. So let's see how this graph changes when the sound being produced is louder. So we want to know loudness. What is loudness? Loudness describes how loud, the volume basically, how loud or quiet a sound appears to us. When we are talking about loudness and volume, we're saying what is the volume basically? What is the volume? So let's see what happens when the volume is higher. When the sound is louder, we say a sound becomes louder when one, the object producing sound, the object producing the sound vibrates more strongly. Instead of grrr, it's grrr. Instead of grrr, it's grrr. There's a louder sound. There are more vibrations. Even my body was vibrating more when I'm saying grrr. My head is not shaking too much. Try it. Let's see. If you say grrr, your head is not shaking too much. But if you say grrr, you feel the vibrations even more. So there are stronger vibrations. So stronger vibrations. Are we together? We know that sound is a vibration. When the vibrations are stronger, what do we get? Louder. Louder sound. Are we together? So what will then happen? You should say the amplitude of the waveform increases. So when we have, you all know what amplitude is. You know. Amplitude is that distance from the zero line to the top, or distance from zero line to the bottom, which is the same. If that distance increases, distance to the top is now more. So it also means distance to the bottom is now more. If the amplitude increases, the sound would be louder. Are we together? So if you are seeing a louder sound on your waveform, you should see a larger amplitude. Are we together? All right. Now, it's all about amplitude. So sound is on loudness is on amplitude. A sound becomes quieter when the vibrations are smaller. When the vibrations are not as huge, they are not strong. Instead of you have instead of the vibrations are smaller, weaker. They're not as strong. The vibrations are smaller or weaker. Yes. And the amplitude of the waveform decreases. Then you have a quieter sound. Mr. Clarify is no longer shouting. So your diagram does not have very high amplitude, very large amplitude. So the center line or the zero line. We also call it the center line. Distance from the center line. Distance from the normal position. That zero line or the center line or the normal position, that flat line. The distance to the peak is the amplitude. Or you can say the distance measured from the center line to the trough, which is the bottom, is the amplitude. Are we together? Oh, all right. So when you have, let's put it here, large amplitude, what is this equal to? Loud sound. Well done. Loud sound. You've increased the volume. What about when you have a small amplitude? What does this mean? This, yes, you have a quiet sound. Low amplitude is equal to quiet sound. Victorson, where are you? Huh? Good. Let's put the waveform. It will be appearing like this on your screen. Large amplitude will be like this. It goes deep and whatever, so it will be deep. Like this. Oh, I don't want to make it too crazy. Let me just make it a little bit normal. Large amplitude. Loud sound. When you have a small amplitude, then you have a quiet sound. Can you see? If we are to put a zero line, it will be like, let's say here, for example, at the center of these things. And you can see that the amplitude is very small. But if you put the center line, if you put the center line here, you can see, wow, this is a bigger amplitude, which means there is a louder sound. Okay? So if amplitude increases, then loudness also increases. Okay? If amplitude increases, then loudness also increases. Loudness increases. That's it. Don't let me down. Okay? Any shortwave is going to be representing a quiet sound. Right? A shortwave will represent a quiet sound. Are we together? Okay. Now, let's do the second and last part. You did loudness. Now you need to know pitch. You can work on the loudness of sound and you can work on the pitch of sound. What does pitch represent? It's not about loudness. We are done with loudness. Pitch is how high or low is the voice. Is it like this? Hello, everybody. So yeah, I'm trying to tell you that. Or is it like this? Hello, everybody. I'm trying to tell you that you should be very, very careful when you're going outside the gate. When you hear a high pitch, okay, it'll be like a child's voice, isn't it? If you have a deep voice, a deep man's voice, it'll be saying, "Hello, everybody. I'm just trying to welcome everybody to the airport. Um, I hope you had a safe journey. Whatever, you can enjoy yourself around the country. Welcome to the country of whatever you're welcoming everybody. But you can also say, hello, everybody. We hope you had a safe journey, and we trust you're going to enjoy your stay here in the country." Blah blah. That's a higher pitch. A bass is a low pitch. Anything which is bass is low in pitch. So a whistle, let's say, what does it have? Does it have a high pitch or a low pitch? A whistle. A whistle has a high pitch. What about bass drum? Good. What about bass guitar? Low pitch. What about lead guitar? High pitch. So the pitch is going to be how high or low that a sound seems. Are we together? Right. Let's see, how do we look at the graph and tell the pitch? You can look at the waveform. So now you know, if you look at the waveform and you see short waves like this, short waves, that means the loudness, that means it's a quiet sound. Right? It's not very loud. If you look at it like this, you say, oh, this person is screaming. Are we together? Vic, are we together? Pitch is, or pitch describes how high or low a sound seems. How high or low a sound seems. Examples of pitch. A whistle. This has a high pitch. Bass drum. This has a low pitch. Child's voice. This has a high pitch. A deep voice of a man. This has a low pitch. Okay? This has a low pitch. Hello, everybody. Yeah, well done. I'm very proud of all of you. So pitch has nothing to do with loudness. Pitch is the voice high or is the voice low? So how do you see it on a waveform? How do you look at a waveform and tell the pitch? What is it that you look at? You just count the number of mountains, or the number of you can say troughs, the number of peaks or troughs that you can see. It tells you the pitch. And that is what we mean, and we'll be calling that frequency. So I want you to say frequency. Frequency. We're saying how many waves do we see in a second? Frequency is the number of full waves or the number of complete vibrations. Frequency is the number of complete vibrations per second. Frequency is the number of full waves per second. Okay? Unit is hertz. Frequency, the number of complete vibrations per second. Are we together? When you look now at your waveforms on the screen, if you see one which is like this, right? Is it loud? Maybe a little bit, not too much, because it's almost spreading the whole screen. What about the frequency now? Give me a second. Give me a second. Wait. Yes, hi. I'm live. I'm live. I'll call you back just now. Okay, sure. Okay. Okay, I got you. Can you all hear me? Right. We'll be saying, what about if you see now one like this? If you see a waveform like this, is it loud? It's almost the same as this one, right? Because the distances are just the same. Can you see that? But what is the difference? Their loudness is the same, because when you are talking about loudness, you don't even look, you just look at this distance. It's actually this one, the amplitude. But you can also use the top to the bottom to just analyze, right? You can see, it's just the same, so their loudness is the same. What is different on these two waves? They have similar loudness, but the pitch is different, okay? This one has a low frequency, which means we are not seeing many mountains. Are we together? So it has a low frequency, which means it is a low pitch sound. It's like this. Hello, everybody. That's what I'm trying to talk about. When I'm trying to talk about this, you gotta understand this. So why does it have low frequency? The lower the voice, the less waves you actually see. Are we together? But when you have a high frequency, we are not looking at the loudness. We are not looking at the amplitude. We are counting the peaks. We are seeing how many. Here we can see only one peak. Here we can see 1, 2, 3. So there's a high frequency, which means this is a high pitch sound. Hello. Yes, that's something like that. We're trying to tell them that. Do you understand? So when you see many close waves together, many waves close together, then you have a high frequency and a high pitch. If you see just a few waves spread out or spread apart, then you have a low frequency, which means you have a low pitch. All right? Loudness, we look at amplitude. Amplitude controls loudness. So this is the last. Write your summary to say, summary, what we have seen is that amplitude of the waveform, amplitude controls loudness. And frequency controls. What does the frequency control, Vic? The pitch. How high or low the sound is. Woo! That's more like it. Come on now. You can do this. So I'm going to give you questions. And remember, oscilloscope is just a device that displays sound waves as wave forms. Isn't it? And waveform is the graph that shows movement of air particles, how they move forward and backward, right? Waveform graph. That, but have you seen that the oscilloscope does not have the center line? Make sure you know that it doesn't have a center line or a zero line. Okay, graph that shows the movement of particles in the air, right? Yes, we know that it starts by, the vibrations don't start in the air. They start wherever at the instrument, the thing that is producing the sound. That's where the vibrations start. And then they move into the air. When their vibrations are in the air, we can see them on a CRO, on a cathode ray oscilloscope. Are we together? When that sound wave is moving in the air. Is there anyone with a question here? I didn't hear that. Yes, the particles in the air are vibrating, which means they are moving the sound wave. Whenever you have a vibration, you have sound, right? Sound is a vibration. So the waveform is proving to you that the particles in the air are vibrating. That is why they go forward, backward, forward, backward, forward, backward, up to here, then forward, back to the same spot, then backward, then like that. So why do they do that? They are vibrating. What does it show? Sound. Are we together? In real life, they are vibrating like this. But we show them on our wave as backward, forward, backward, forward, and that's your waveform. When your vibrations are tall, like this, that means it's louder. When your vibrations are short, that means it is quieter. When your vibrations are close to each other, that means it's a high pitch. When your vibrations are widely spaced, that means it's a low pitch voice. So don't forget, don't let me down. I need you to maximize. Get 100 for this. Are we on the same page? Thank you. Let me give you questions that I want you to do right now.